Hi everyone. Thanks for listening. I'm here to talk about affine patches of open positroid varieties. And so just we'll take a step back and we'll just remind everyone of the Riemannian. These are all k-dimensional subspaces of C to the n. And I'll be thinking of these as row spans of full k by n, full rank k by n matrices. And what we'll do to these matrices, we'll assign Fluker coordinates. So these are going to be determinants of maximal k by k matrices. So as an example here, I have X is the row span of these two three-dimensional vectors. And I have three Fluker coordinates. So delta 1, 3 will be the determinant of the matrix spanned by the first and third columns. Okay. And it turns out it's easy to show that row operations will change all of the Fluker coordinates by common rescaling. So this gives us an embedding into the projective space that Melissa talked about. And what I want to do is I want to define open positroid varieties. Alan defined them a bit using these bounded affine permutations, but I want to just have us understand them a bit more easily. So if you've never seen these before, these open positroid varieties are essentially intersections of where we require some Fluker coordinates to vanish and some to not vanish. Or you can do it Alan's way of looking at when some matrices have this bounded affine permutation, right? Using that site-swap way. So what do we know about open positroid varieties? These are pretty well studied. What do we know about them? Turns out we know a lot. And this is not even the whole story. This is just some of the story. But there's a lot of nice combinatorial diagrams and combinatorial ways to understand a lot of the structure of these positroid varieties. So as an example here, we have Deodar diagrams. These are pipe dream looking objects that help us encode the point count of these open positroid varieties. These are essentially visualizations of Deodar subexpressions. We also have Richardson links here. These are links associated to my positroid varieties, or in general, really just to open Richardson varieties, which help us understand some cohomology of these open positroid varieties. So these invariants help us understand these varieties. There's also a relationship to Catalan combinatorics. So Galatian and Lamb showed that a certain subset of Deodar diagrams are counted by rational Catalan numbers. They prove this bijectively for the Catalan case. I have a recursive proof in the Fus Catalan case, but in general, there's no direct bijection in the rational Catalan, so that's kind of interesting. There's also these Plavit graphs and ley diagrams. So these are very intimately connected. Plavit graphs have a lot of nice history when it comes to the study of total positivity that we just heard about. And also they help us compute help us understand the cluster structure of these open positroid varieties. So these are a cluster algebra, a coordinate ring cluster algebra. And the ley diagrams help us create a reduced Plavit graph. That's it. And this is the work of a lot of really amazing mathematicians. This is not at all a complete list. These are really very well studied. So the question I have is, okay, we have that these open positroid varieties have some subsets that are required to vanish, some subset of Flukers, another subset that are required to not vanish, and then a third subset that can be free. So my question is, what if I look at one of those Fluker coordinates that are free and I require one of those to not vanish? What happens? So this is the subvariety of an open positroid. Well, it's a theorem of Michel Snyder that this is actually isomorphic to an open affine Richardson variety. You've heard of those. To me, this is a bit surprising. I mean, naively, perhaps the affine flag seems a lot bigger, but in some cases, these open affine Richardsons are subvarieties of normal open Richardsons. So to me, it's a little surprising. But this helps inform us with our next steps. And the goal, the idea is to generalize a lot of the previous combinatorial objects to this setting. And so the question is, what can we do? And the answer is quite a lot. So I added a lot of the words affine here because we're now in this affine setting. And the moral of the story, I'll explain the pictures in a moment, but the moral of the story is everything lived in like a disk, and now we're living in a cylinder. So for example, these affine Deodar diagrams, these do the same thing morally that these Deodar diagrams do, except in the sense that they help us compute point counts, for example. But now they live in this cylinder. So for example, this wire here will connect down here, and we can imagine it either as this like infinitely long diagram or just with this representative region. Okay. We also have these affine Richardson links. So this is the only thing that my computer can't draw for me just yet. But essentially, it's a very, the moral of the story is the same, where we want to associate a link to these patches and help us understand a lot of structure. Okay. Because of the fact that they live in a cylinder, we have these weird looping gradients. We also have affine lay diagrams here, which are the same as the standard lay diagrams, except now they live in a cylinder, as I mentioned before, which help us compute punctured Playback graphs. So you can imagine them in one of two ways. You can imagine them as a Playback graph where I took a face and I just ripped part of that face and unraveled things. Or as a cylindrical Playback graph where all my boundary vertices are on one side of the boundary. And there's also a relationship here to Catalan combinatorics in the sense that there's a lot of nice bijections in the affine diorder diagram case. Some of these use ideas from statistical mechanics. But yeah, so it's a very nice story here. So I just want to give an idea of what kind of theorems that we obtain. I also want to mention this is joint work of, some of this is joint work with Alkin, who's here, and my academic sibling, Matthew Tyler, and this does build on a lot of work of Michelle Snyder. She introduced what are called affine pipe dreams, which are what you maybe expect, where I have reduced pipe dreams here. Affine diorder diagrams are generally non-reduced. But as an example of what kind of theorems that we have Postnikov proved that there's a way to associate lay diagrams to a class of reduced Playback graphs, and we can do the same thing with punctured Playback graphs. Just as a note, this should be filled with the dots. If you know the rules for lay diagrams, it essentially says that if I have, I'll draw it. I have to be closed under this backwards L. That's why it's called lay for backward L. So this is a taste of what kind of theorems that we obtain. Thank you. Questions?
Can you use either the affine lay diagram or your punctured Playback graphs to parameterize like positive part intersected with this affine?
That's a good question. We haven't thought about positive parts yet.
Yeah, I mean, I guess they're contained in.
Yeah. So it's just haven't really either. They're kind of contained. We haven't thought about too much about positivity.
Time for one more question. Did you have a? Just sort of confused about something. So in the statement of the problem, we want other intersections. Why is that different than it's like they're considering sub-varieties?
Say it again. Why the different intersecting?
Like just including it in the set BF.
Right. Yeah. So if I just chose B, then this would just be the same as just being the standard open positroid variety, right? And actually, that's a good question because of something else I wanted to mention quickly is if I had chosen one of these index sets to be one of those Bs, it's very easy to show how you obtain the standard stored. So there's a very nice bijection in many cases. So for example, in the links, you can use Reitermeister moves to go back to the standard Richardson links in that case. All right, thank Tom again.